Let's meet the guy who's going to scare the P1 out of us. Dr. Joe has brought his family up, CalTech scientist, deputy principal investigator for NeoWISE, which is coming to an end within the next 2 months. He'll tell you about it. Called the Hunting for Hazardous Asteroids Using Infrared Light. He's a research scientist at IPAC, research organization at CalTech, and the deputy PI on the NeoWISE mission focused on studying the physical and dynamical properties of asteroids, those dreadful rocks, using a range of techniques like photometry, polarimetry, numerical simulations. Joe received his BS in astronomy and astrophysics from Penn State and his Ph.D. in astronomy at the University of Hawaii. And he's agreed to take formal questions afterward, unless you're so pushy like some of us are that we interrupt when he's to take those too. Ladies and gentlemen, Joseph Masiero.
All right. Thank you all for coming. Let me get this all sorted out. So, share my screen. Let's see if this. All right. How's that looking online? Good? Looking good. All right. And everyone can hear me? Am I loud enough? Excellent. All right. Well, thank you all for coming tonight. Thank you for the invitation to speak. I'm really excited to get to share with you the work that we've been doing over the past years looking for hazardous asteroids. My work has involved the NeoWISE Space Telescope, where you can see a nice illustration of it here. In fact, I joined the NeoWISE mission 2 months before it launched from Vandenberg Air Force Base, right after I finished my PhD. And so I've been working on NeoWISE for nearly 15 years at this point. It's been a major part of my career, and it's really exciting, all the cool stuff that we've seen, all the great discoveries it's been able to make, and getting to realize what it's revealed to us about our solar system and our place in the universe. So before I start, I just want to talk about what IPAC is. So as Ron said, I'm a research scientist at IPAC. Nope, that's not it. All right, I don't know how to get rid of that. Oh, anyone know what it is? Let's see. Hide. Aha, figured it out. So IPAC is a research organization at CalTech. It started out as the data processing center when the IRAS satellite was launched around the time I was born in the early 80s. And it grew, it was part of JPL, it moved down to CalTech campus. And it's hosted a variety of all-sky surveys and infrared data. It started out as a specialty research group for processing, analyzing, and archiving infrared data. It's grown since then, but some of the wheelhouses include the IRAS data, the 2MASS data, which is the 2-micron all-sky survey, WISE, which you can see the all-sky map in the bottom left, the Planck data. It was the Spitzer Science Center, so the main nerve center for all of the Spitzer science images, the Herschel Center in the US. It hosts NASA's Exoplanet Archive, and it's working on new future missions like Roman Space Telescope and Surveyor. And so that's this research organization. IPAC used to stand for the Infrared Processing Analysis Center because we've grown to more than just infrared. We are now just IPAC. It doesn't stand for anything. It's just IPAC. So that's what IPAC is. We're located on CalTech campus. We are south of the gym, where if you've ever been to CalTech campus, every time I say that to someone, they say, I didn't know campus went south of the gym. And I say, no one does. And so we don't get any visitors, which is perfectly fine because we get to just do our work. So it's a really nice facility, and it hosts all of these data archives that I'll tell you about a little bit later as well. So asteroids and comets, what are they? These are the building blocks of the solar system. They're the leftovers from the formation of our planets. And so through the study of the asteroids and the comets, we can get a better idea of how the planets formed, what was going on at that time, 4.5 billion years ago. What have the planets experienced since then? What are the forces and the events that have occurred in the last 4.5 billion years in our solar system? And how does this relate to the dust cloud that originally formed our sun and our planets? And what does that mean for life on Earth? I like to show this image. This was put together by Emily Lakdawala of all of the asteroids at the time she made this that we had visited with spacecraft. And what's really nice is that they're scaled by the size. So they're the correct size, but they're also the correct color. And so this is what it would look like if you went up to them. They're all gray. Asteroids tend to be just gray chunks of rock, but they span a range of brightnesses from Lutetia, the big one on the left, that's as reflective as a sidewalk, to some of the darker objects down here in Matilda, or the comets that we visited at the bottom here, that are the color of fresh asphalt. And this coloring, even though it's a fairly general overview of what they are, tells us a lot about the formation. But I was mentioned earlier to some of the guys I was chatting with, the solar system, these small bodies haven't experienced the same kind of weathering, the same kind of events that we've had on Earth. Earth was fully melted at some point in its history. And so the mineralogy is incredibly complex. We have volcanoes, we have sedimentary features, we have metamorphic rocks. Asteroids have none of that. And so there's only a finite number of different minerals that you can build from the components that are available, from the heat and the pressures that are available. And so even a simple metric as how bright are they helps us figure out what they're made of and gives us hints about where they came from. One of the things we've learned is those dark objects here all have significant amounts of water bound up in the rocks. Even if they're not comets, they are a reservoir of volatiles. And it is likely that they are the source of the water on Earth today, and therefore of the oxygen and the carbon dioxide in their atmosphere. And the ability for us to have life at all was because these asteroids, especially these dark asteroids, trapped a lot of it at the beginning of the solar system. So this is a top-down view of our solar system. I show a lot of plots like this, so I just want to introduce this. The sun is the yellow star at the middle. The cyan circles are the orbits of the planets from Mercury out to Jupiter. And every single dot is an object that was in the catalog at the time the image was made, at the position it was at that moment in time. And so each of these objects is being tracked by the Minor Planet Center. The green ones are the main belts, the reservoir of asteroids in between the Mars and Jupiter. The blue ones are Trojans. These are things caught in a gravitational resonance, a dance with Jupiter. For the last 4.5 billion years, they've been captured there and haven't gone anywhere. And all of the red dots, every single red dot you see there is a near-Earth object. One of the ones that potentially could pose a hazard to us that we have to pay attention to. So there's a lot going on here. Of course, these points are much bigger than they are in real life. This is not like Star Wars where you see asteroids ever. If you were standing on an asteroid, the next nearest asteroid would be just barely visible to your naked eye. So there's a lot of empty space in here, but there's a lot of things going on, a lot of things we have to chase. Yeah. The Minor Planet Center is the internationally recognized organization that maintains all of the orbits of all of the minor bodies, the asteroids and the comets. Everyone in the world who takes a measurement of a position of one of these objects sends it to them, and they compile it and say, here's the orbit of the object, and it's their job to keep track of it, to archive it, and to publish this for the world to go to. And so they are the clearinghouse for all asteroid astrometry and comet astrometry. So this is what the solar system looks like today, about 1 million known asteroids and comets, but it didn't always look like this. In fact, about 200 years ago, this was our view of the solar system. This is all we knew about. We knew about the 7 classical planets, and a few years before 1800, William and Carolyn Herschel were doing a survey of the sky, and they noticed something out there. In fact, they found a new planet. First time in human history that someone had found a new planet. And they named it, of course, the most obvious name, Gregorius Sidereus, King George's planet, because that's what you do, you acknowledge your sponsors. And so after that, they decided to change the name. There was a lot of the people who weren't in England were a little upset by that name, considering they didn't really like King George. So they gave it a name that has no drama associated with it, and they called it Uranus. So they found Uranus, and that led us to say, well, if we found one more planet, are there others out there? And that awkward gap between Mars and Jupiter had bothered people for a long time for reasons that were not necessarily mathematically or physically relevant, but people thought there should be something there, another planet that was missing. And so searches were conducted, and they started finding things. They found a planet in the gap, and they said, great, we're done. And then they found 3 more, and they said, okay, well, there's 4 planets in this gap. And then they found another one, and then they found more. And we got up to around 33 planets in the solar system before we realized that this was not a planet or a few planets. It was a belt of bodies. And so all of these planets got demoted and were called asteroids, star-like things that happen to be moving. And so you'll see as we get on through the 1900s, we start getting a few more objects. And then all of a sudden, you'll see a pulse of objects. Right now, as a few targeted surveys were done. And then as we move to CCD cameras, you'll see the numbers suddenly ramp up as we found more and more objects. As cameras got better, reporting got better, computers got better. But what really happened, three big things happened in the 1990s that dramatically changed our view of the solar system and drove a massive increase in the number of objects. I said CCD cameras were one. The other one was that we've had a few major discoveries. We found the crater off the Yucatan, the Chicxulub crater, was recognized to be an impact crater associated with the end of the dinosaurs. And that around the same time, a comet smashed into Jupiter. Shoemaker-Levy 9 hit Jupiter and said, hey, there are things out there and they hit other things and we should pay attention. But the most important thing that caused this major uptick in the number of asteroids we discovered and the desire to do asteroid surveys was the release of the movie Armageddon. I'm not kidding. It drove a major interest in the public that asteroids could hit the Earth. Some of you remember there was another movie at the same time called Deep Impact, which actually was much more scientifically accurate. However, it didn't have Bruce Willis or Liv Tyler or Aerosmith singing the song, and so it was totally unnoticed. So moral of the story is if you want to sell something, put some big names in there, but I guess Hollywood figured that out a while ago. But this is where we are today. Because of all of this, because of being better technology and better public awareness, we have more surveys looking for more asteroids. And my part in this was working on the NeoWISE mission. So NeoWISE was a reactivation mission. We took a spacecraft that existed and we brought it back to continue a specific asteroid survey. This was led by Amy Mainzer, who's a professor at UCLA, under NASA's Planetary Defense Coordination Office. Lindley Johnson was running it for much of the time NeoWISE is active. He recently retired and is in an emeritus position. But we utilized the WISE spacecraft. We took it out of hibernation in October of 2013. We were focused on the two shortest wavelengths that still worked, the 3.4 and 4.6 microns, which we called W1 and W2. And this is passively cooled. We were just subject to the whims of nature and the heat flux from the sun and the Earth. And so we were floating at around 75 Kelvin for much of the life. We didn't have any propulsion, so we continued the survey as WISE surveyed the sky. And so we started collecting scientific data in December of 2013, and we recently ended the mission this past July 31st. We stopped science data collection. On August 8th, we decommissioned the spacecraft, and it is currently inbound. It's spiraling inwards. The sun has caused the atmosphere to puff out, has increased drag, and it is spiraling in faster and faster. It will likely re-enter the atmosphere sometime around mid-October to mid-November, and it is expected to entirely burn up. Possibly something the size of a fist might make it through, but it's unlikely. So I've seen this mission through a large phase of this. Now, the goals of NeoWISE specifically were to conduct a survey for near-Earth objects, to discover new ones, but most importantly, to provide physical property characterization. Prior to WISE's launch, we only knew the sizes of about 2,000 objects. We only knew about 2,000 objects, how reflective they were. After WISE launched, a year later, we had 150,000 objects that we measured sizes and reflectivities for. And so this major change in what we knew about the solar system was provided by doing a survey in the infrared from space. Now, I said NeoWISE used the WISE spacecraft. WISE was launched in 2009. It was originally an astrophysics mission. It was in the Mid-Class Explorer, and its goal was to do a 6-month survey of the entire sky at 4 wavelengths. Those same two short wavelengths, 3.4 and 4.6, as well as a 12 and 22 micron. These are way out in the thermal infrared. So we had a 40-centimeter primary mirror, about the size of a pie tin, and it was cryogenically cooled with solid hydrogen ice, which is exactly as dangerous as it sounds. And it kept the telescope at a few degrees above absolute zero. And that is what allowed us to look at 22 microns, to take images at the wavelengths that generally things that are warm emit light at. So we launched December 14th, as I said, just down the street here in Vandenberg, onto a polar sun-synchronous orbit, and we were just sweeping out rings of the sky, taking a picture every 11 seconds, snapping through the sky, building up rings. Over 6 months, that ring swept out a whole map of the sky. And this was led by our PI, Ned Wright, professor at UCLA. Now, we had 3 goals on the WISE mission. It was finds the most luminous galaxy in the universe, find the coldest and closest brown dwarf stars to our sun, and to make an infrared atlas so that James Webb knew where to point. James Webb is an incredibly powerful telescope, but it is looking through the tiniest of soda straws. And so until you know where to look, you don't know where to point it. So we built a map that gave scientists an idea of where they should propose looking with James Webb. And so that is this map you're seeing on screen right now. The blue color here is the 3.4 micron. The green is the 12 micron, and red is the 22 micron. What you can immediately see, this is a galactic projection, so that's the Milky Way cutting across the center there, is the dust bands that I'm sure you all are very familiar with are gone. That the stars, every single blue thing is a star. Even red giant stars are blue in these wavelengths. That green is the dust glowing from being room temperature. And some of the red dots you'll see down there are even 100 Kelvin or less than a few hundred Kelvin in temperature. And so what blocks optical light is glowing at 12 microns and is completely transparent at 3 microns. And this is why you do infrared surveys. Another neat thing, you can instantly see the bulge at the center of the Milky Way in this wavelength. It's without a question, you can see that there's a disk and a bulge. Something that took a long time to prove using visible light is instantly apparent at infrared wavelengths. So you notice none of those said anything about asteroids, about moving objects at all. And in fact, the original plan was to throw that data away, was to just take the repeated images of the sky, stack them together, make a deep image, and that was the final product. And so NeoWISE started life as a software add-on, saying, hey, let's catch that data as it's coming in, let's archive those single frame images, and let's look for things that are moving. And so what we're showing here, this is one of those stacked images, but instead of doing a median combination, we just add them together directly. And so these chains of green dots are the asteroids moving across the field of view in front of the nebula here. And so this is what we were looking for. This is what our software pipeline was trying to find. And we did a fabulous job because infrared is incredibly powerful for looking at asteroids. So this movie is showing, again, that same top-down view of the solar system, stepping through week by week as NeoWISE scanned the sky. Every single dot you see there is an object that we observed with our survey and reported in real time to the Minor Planet Center. The green and the red points are near-Earth objects. Black are the main belt objects, where there's just too many to keep track of which ones were new and which ones were previously known. And all of the squares you see, the cyan and the yellow, are comets. And so you can see the red points and the yellow squares are things that were discovered by our mission in the course of this survey. And so as we swept out, one thing you'll notice is that those red and green points are like a swarm of bees hanging out around the Earth. This is not because asteroids like the Earth. It's because the racetrack analogy, where as you're going around a racetrack with cars moving about the same speed, it takes a long time to catch up to something on the far side of the track. And this is what encouraged us to say we could do more. If we're allowed to continue our survey, there are more asteroids to find and measure on the far side. If we continue that survey for typically about 10 years, is how long it takes for you to sweep up that entire space. And so this was again, at the end of this movie, this was our top-down view when we put WISE into hibernation. And it's what allowed us to demonstrate that we were great at finding asteroids, characterizing them, and that there was more to do, and so that reactivation would be beneficial. So when we turned the mission back on, we took a picture from before reactivation, before we put it in hibernation and after, and it turns out despite being in space for 2 3/4 years without any power on, without anything going on, there was no degradation of the detectors, no degradation of the mirrors. And this really, again, encouraged us that we could continue our survey. So originally we proposed for 3 years to finish up in December of 2016. But as we got closer to that, we realized there was more to do. And the atmosphere had been benign. I don't know if you're aware, but the last solar minimum was incredibly long and incredibly quiet. And so the atmosphere was not puffed up. And so we had significantly longer life than we ever anticipated when we asked to reactivate the survey. And so we just kept going back every year or two. Hey, we think we can squeeze another year out of it. And so that's how the mission went until this past July, when we finally said, I think we've hit our end. So this movie shows that same top-down view, but now instead of 1 year, it's going to swing through, I believe this is 8 or 9 years of data. So it's going to go real fast. Each of the white flashes is the first observation of an object. And you can see how busy the solar system is, how there's still a ton of things out there. And that swarm of bees of the green near-Earth asteroids is starting to spread out. We're starting to sample that entire population. And so you can see in the bottom right corner, okay, so that ended in December of 2022. So in total, we detected over 42,000 objects during our activation survey. And we've detected in total around 3,000 near-Earth objects, which is about 10% of all the known objects out there, primarily the bigger ones, which allow us to characterize the population. Now, how do we use infrared light scientifically? Why is it so powerful? What I'm showing here, this is a spectral energy distribution. So how much light you're getting from a target as a function of wavelength. So wavelengths on the bottom here in microns, and the flux in Janskys is going up and down on the y-axis. The left is a near-Earth object. So the temperature of the body dictates how much thermal light it emits. Something's warmer, it's brighter in the infrared. And so on the left, the near-Earth object is pumping out energy at the W3 and W4 wavelengths at this 12 and 22 micron bandpass, but still is rather bright, is significantly brighter than it is at optical wavelengths down here. Each of these colored lines is a different color of object, with the bottom one being something about the brightness of coal, and the one at the top here being the brightness of chalk. And so while the reflectivity, the albedo of the object, really changes how much light you get from it in optical wavelengths, it makes almost no effect in the infrared. And this was the power of an infrared survey, is that we're insensitive to how bright it is. We only care about the temperature of the object. NeoWISE was wise when its cryogenic mission was incredibly good at seeing objects all the way through the main belt. But you'll see that as we got into the post-cryo mission, we're just on the two shorter wavelengths, it had a harder time as you got farther from the sun. Luckily, that was not our mission. Our mission was to focus on near-Earth objects, and so our sensitivity was just as good in the near-Earth space. And that's what allowed us to continue this mission, despite losing that cryogen mission, the cryogenic coolant. Here I'm showing the sizes that we measured for all of the near-Earth objects we discovered compared to their visible albedo. Again, that's reflectivity. So stuff at the top here is like sidewalk. Stuff at the bottom here is like dark asphalt. And what's interesting is all of these black points are things we discovered in our mission. And you can see that some of them are getting up into that couple kilometer range. Incredibly dark, but the size of the thing that killed the dinosaurs. And so I personally think it's a good idea to keep track of where these things are and that we know about them. Here's the census. I took our data set that's public online.
It's 88 out there.
The Chicxulub impactor was, I believe.
Okay, I'm in the middle of a Zoom meeting here, so.
Oh, me too. I'm in the middle of a Zoom meeting. Someone's talking to me on the Zoom, so yeah. The Chicxulub impactor was around 6 to 10 kilometers, we estimate. That's based on the size of the crater. The crater is around 100 kilometers across. And so typically the crater is 10 times bigger than the impactor. So this is taking all the publicly available data, putting where they are in the solar system, coloring it by how reflective it is, and the size of the point is the size of the object. And so you can see the trends across the belt here. Here we have stuff that's very bright. As you get farther in the main belt, you get more of these blue and black points. Those are the water-rich asteroids. Out here are the centaurs. These are the objects stepping inward from the Kuiper belt through the giant planets that will eventually one day become Jupiter family comets. And so this is all the data we collected during our initial mission. So all of this has been great, but why near-Earth objects? Why do we care about these? This is Itokawa. It's the first near-Earth asteroid, or the second near-Earth asteroid we visited, but the first weird one. And what I really love about this is just how strange Itokawa is, because this is not what we expected. When we went to Eros, when Galileo flew by the first asteroids we saw, they looked kind of moon-like. They had dusty surfaces, they had small craters, they looked kind of what we expected. They were a little lumpy, but they fit our storyline. And then Hayabusa got to Itokawa, and it looked like nothing we'd ever seen before or even expected. This looks like a pile of gravel with these low-lying dusty areas here with a boulder, this giant boulder just sitting off the edge of it. There's what appears to be two lumps here, one smaller and one bigger. This looks like a pile of gravel. And that's because we think that Itokawa is a pile of gravel. After further analysis, we've determined that Most of the small objects probably are collisional reaccumulations, that asteroids were born at tens or hundreds of kilometers in size. And anything smaller than that is the result of two things crashing into each other, spitting off a bunch of gravel that gently reaccreted. And so this body is not held together the way planets are. It's not structural in any sense. It would flow and move if you stepped on it. So they're weird. And interacting with something like that will be difficult. Asteroids, as you may have guessed, are an impact hazard. This is a fireball plot put together on the JPLC NEO's website, showing all of the impacts recorded by, I love the top here, US government sensors. These are satellites that they are monitoring for nuclear tests, nuclear bomb tests that are illicit. And so they're constantly looking around the sky, looking across the Earth, and they happen to see asteroids that are coming in, blowing up. The one right over here, so right just off the Philippines, that's the one that 2 days ago was discovered in Pacific time around 11:30 Tuesday night, our time. I got an alert that was sent out to a broad wave of people saying, hey, we found this thing, it's a little suspicious. Went to bed, and by the time I woke up the next morning, there were about 20 more emails as follow-up observers around the world had measured it and determined that, yes, it was going to impact us. And it hit Wednesday morning, 9:30 a.m. Pacific time. So it was around 2 a.m. in the Philippines. And they were in the middle of a typhoon, but we had enough warning that people were able to go outside and hold up cell phones and take photos of the thing coming in. It's really cool. So we are starting to get to the level. Obviously, we haven't predicted all of these, but we're starting to get to the level where that's a possibility, that we can respond to these in advance. What's the big red one? My next slide is the big red one. The big red one is in February 15th, 2013, an event happened in Chelyabinsk, Russia. This was a massive asteroid, probably about 15 meters across in size, that came in the daytime sky, flashing through the sky, and every second for 30 seconds released about 10 kilotons of energy. The same energy as 10 kilotons of TNT. And so it was exploding through the sky. And we had instantly, within hours, there were videos all over YouTube because Russia has an immense amount of insurance fraud. And so everyone has dashboard cameras to make sure no one hits their car. And so all of these got uploaded. And so you got massive videos from all around Chelyabinsk about this bolide that came in and exploded. It shattered windows. It injured about 1,000 people because, unfortunately, nowadays, well, I guess fortunately, unfortunately, some of the older members of the audience may remember that when they were kids, you had those nuclear bomb drills in school where you hid under the desk because your desk was nuclear bomb proof, right? It's because, as I'm sure you all know, light travels faster than sound. And so when you see the flash in the sky, that's great. The shock wave comes a few minutes later, and you want to be under that desk when the roof collapses on you. Now, we don't do that anymore in schools, so that's a good thing from one point, but people haven't learned the lesson. And so what happened was when they saw a flashing light in the sky, everyone did the natural thing of pull their phone out and walk up to a window to get a good photo. And so they were in a perfect spot for the blast wave to blow shattered glass. So there were a lot of injuries, no deaths that I knew of, that we've heard of so far. But there were also tons of pieces of the meteorite scattered across the ground. It was February in Russia. It just snowed. And so people would go outside and see these little finger-sized holes. At the bottom of them, they would find little BBs of rocks, just like this one. And so this is a piece of that Chelyabinsk impactor that I bought online because that's where you buy everything nowadays. But yeah, there were a ton of these meteorites coming through. We didn't know about this in advance. And what's really disturbing is what they do in Chelyabinsk. Does anyone know what the primary industry of Chelyabinsk is? There you go, nuclear weapons. In particular, that is one of the cities that didn't exist on the map until after the fall of the Berlin Wall. It was comparable to what we would do in Oak Ridge, Tennessee in the US. It was nuclear material refinement for weapons. So had this happened in the 1960s instead of the 2010s, it might have been a very different story if you said that there was a nuclear grade explosion in the skies above one of our major weapons facilities. People on the ground reported that it sounded like they were under attack because they had the giant kaboom and then it sounded like gunfire surrounding them. It was actually the echoes of that kaboom off of every tree and mountain for dozens of miles around them, but it sounded like gunfires. And so that would have been a very different phone call had it been during the late 60s, for instance. So one of the good reasons to make sure we know what's going on in the sky around us. And of course, because it's an asteroid talk, I have to talk about the dinosaur killer and I have to put a fun image of the giant comet or asteroid that smashed into the Earth and darkened the skies for years and caused the extinction of the dinosaurs, except for the birds, but we don't talk about that. And left us with enough space for the mammals to grow into humans. So yeah, go Ash. I guess I like the asteroid killers for that. I don't know. Anyway, but asteroids are not just a hazard to Earth, as I referenced before. In 1994, Shoemaker-Levy 9, that's a typo. Shoemaker-Levy 9 impacted Jupiter. It was a comet that was discovered by Eugene and Carolyn Shoemaker and David Levy. And the three of them noticed this comet that had a swing by Jupiter and was torn apart by Jupiter's gravity. And a few years later, it was going to come right back and crash into Jupiter. And we had no idea what was going to happen. So we pointed some telescopes at it just to see, just in case it was vaguely interesting. And what happened was this small comet, again, a couple kilometers in size, each of those little pieces made a dark splotch on the surface of Jupiter the size of our planet. Each of those black eyes is the size of the Earth. Down here, we have an infrared image from the IRTF on Mauna Kea in Hawaii. You can see hours after the impact, the residual heat, the glow of that heated up atmosphere from that impact. And so these have significant effects on the planets that they hit. But not all comets are bad. Some comets are fun. My favorite comet is Comet NeoWISE. I bet you can't guess why. But we discovered that about 2 weeks after all the lockdowns, I was sitting at my kitchen table and we were flipping through the new images from the telescope, and the group of us were all online in our various homes, and we all happened to find this new fuzzy looking blob. And when we reported it, we said, hey, that's going to be kind of fun. That might get close to the sun. I wonder how bright it'll get. And as many of you know, it got naked eye brightness. It's the best naked eye comet we've had in the Northern Hemisphere since Hale-Bopp and Hyakutake. And, it was visible naked eye in July of 2020 at a time when we really needed some good news. So, it was a nice to go out. We went out to up the Angeles crest and above Los Angeles the first night. And a little bit later, went out to the Mojave to take some photos of it. So it was really cool. And what's really great is when Hale-Bopp and Hyakutake came by, cameras were rare. Nowadays, everyone has cameras. And so the Astronomy Picture of the Day site was full of images from around the world of our comet. In particular, like that center one that was taken by the astronauts on the space station of our comet off the limb of the Earth. You can see it right over there. It's right here, right there. So, the astronauts were leaning out the window taking photos of our comet from the space station. I thought that was really cool. So I mentioned before that we archive our data. This is a public archive. All of our data, every image we've taken, every source we've measured is available for you to use. It is on a free public archive. It's at the Infrared Science Archive that's hosted at IPAC. You can see the URL at the bottom there. All of these are yours. They're taxpayer funded. They are your data. They're your images. Use them. I've seen people who've taken some of our data and done really nice astrophotography style stacks using the infrared or mixing optical and infrared light together to get pretty cool images of various things in the sky. So I encourage you to check out the data and play with it and use it. You can also get the data from the Planetary Data System. This is where you get the sizes and the albedos of asteroids. If you want to use that, you can see the URL for that at the bottom there. So what's next? NeoWISE is over, but we don't know where all the asteroids are, and they still pose a hazard, as we heard about 2 days ago when the small, 1.5 meter object hit us. So what do we do next? Well, we've learned a lot from NeoWISE. Again, it was not purpose-built for asteroid science. So if you ask the question, what do you do? What do you get if you purpose-build a telescope specifically to be excellent at discovering asteroids? If you make that its primary mission, what you get is the Near Earth Object Surveyor mission. And so that's an illustration of it on the left there. It's not much bigger. It's only 50 centimeters in diameter. But what we've done is we've changed up. We have different detectors that are able to be passively cooled. but still operate out to 10 microns. So we get that fabulous sensitivity to asteroids, but we don't have any onboard cryogens to run out. We're going to put it at the Earth-Sun L1 balance point. It's about 6 linear distances away so that we don't have the heat load from the Earth warming up the telescope. We have this new detector technology, these Mercator that are in 2 different channels simultaneously, so we can basically take a temperature of every object we see. And so we're anticipating that we're going to detect around 300,000 near-Earth objects compared to the 30,000, 35,000 currently known, and around 8 million main belt objects compared to the 1 million currently known. This will expand on the results of NeoWISE, and it will help us better understand the kinds of hazards that these objects pose to us and really allow us to check that box off. Is there something that's going to have a major global devastation coming for us? So our goal, find 2/3 of the objects within 5 years, find 90% of the things larger than a football stadium in 12 years, and to measure enough of the smaller objects that we can statistically say what the chance of impact is. As I said, we're putting it at the Earth-Sun Lagrange point, but that very sharp, pointy geometry you saw of the spacecraft allows us to point very close to the sun. So, there it is. So we're able to look down to 45 degrees away from the sun. This is in the daytime sky from the ground, but it means we're able to survey along the Earth's orbit. Things most likely to hit the Earth are going to spend a lot of time near the Earth's orbit. And so surveying where the hazardous things are is a good idea. So we're designing the mission to cover a much wider field of the sky than NeoWISE ever could, while being able to observe in the infrared that NeoWISE demonstrated was great for finding asteroids. So this is a plot like I showed before, the spectral energy distributions of 3 different near-Earth objects and our 2 band passes we're using, both of which allow us to constrain that thermal curve. The other nice thing, this thin line here is associated with this left axis here. It's the number of stars you expect to find that are in a given area of sky that are brighter than your asteroid of interest. And what you see is this is really high. There's a lot more stars than asteroids out there at optical wavelengths. But when you get out to the infrared, the stars go away. They're all significantly fainter. The sky is full of asteroids at infrared wavelengths. And so when you look up, they're the primary thing that you see. And so this is why we focused on these wavelengths. So here's another top-down plot showing the Earth's orbit around the sun. And we're going to show the first 5 years of survey that we planned for Surveyor. And so because this is purpose-built, because this is specifically to do asteroids and nothing else, we don't have to negotiate cadence. We get to optimize our cadence to be ideal for finding asteroids. And so we're just going to pick our cadence, do our observations, and continue this over and over and over again, sweeping out huge chunks of the sky to measure all of these objects. This, again, is showing each of these dots is a potentially hazardous asteroid. That is a near-Earth object larger than 140 meters in size. There are about 10 times as many near-Earth objects we'll see that are smaller than that size cut, and 100 times as many objects in the main belt and further. So as swarmed as this plot is with objects, there's going to be 100 times as many things out there in the full survey that we detect. So in closing, NeoWISE has provided a treasure trove of asteroid data and comet data, as well as stars and galaxies. I didn't even go into all the great work being done on time variable stars, galaxies that are pulsing, watching stars swallowing planets or exploding, all of which has been possible because of NeoWISE's long time baseline and consistent survey strategy. Near-Earth objects trace the physical and dynamical processes that sculpted the solar system. And so by understanding them, we understand our place in it and where the Earth came from. Infrared is ideal for allowing us to get the physical properties of these objects quickly and to allow us to make an unprecedented catalog of the solar system. Albedos in particular provide crucial information on composition and allow us to trace both the collisional families these are part of and the volatile content that from pointing to where they originated. And Surveyor is going to allow us to find over 90% of the potentially hazardous objects and allow us to check that box off to say, this is the one hazard that we're presented with as a species that we can rule out possibly. We can't rule out hurricanes or earthquakes or tornadoes, but we might be able to go out and say, yes, we are certain there's nothing out there hazardous to us. Or if we find something, be given 30 years of warning to do something about it. Thank you. Q&A. Do you want people to use the microphone or?
Did you know in advance that Chelyabinsk was inbound?
We did not know Chelyabinsk was inbound. It's a little bit too small to be detected by most of the current surveys, and it came at us from the direction of the sun.
Oh, okay.
Actually, NASA had a press conference that day about a different asteroid that was having a close pass with the Earth. And so those guys had some very uncomfortable questions about, oh, so you're here to talk about that thing? I'm like, no, we're here to talk about this one, which is different from that one.
So the one that was called Apophis.
Yeah.
Is that, how much damage would that do compared to the KT boundary event?
So yeah, the KT boundary event was around 6 kilometers in size. Apophis is around 300 meters in size, significantly smaller. So if Apophis is not going to hit the Earth, we have ruled out impact possibilities for the next 100 or so years. If it did hit the Earth or something in that size hit the Earth, it would not be a global extinction event. It would just be a very bad day for the Eastern Seaboard or for a few smaller countries. Okay. So, just the collapse of the global economy, not all life on Earth. So, simple little stuff.
I gotta say, let's get this to you.
Feinberg has a question. If we find an inbound dangerous asteroid or comet, what are some of the options that we have to deflect it?
So what are the options for deflecting something inbound? If you saw the DART mission, that was NASA's and the globe's first attempt at trying to figure out, could we move an asteroid, but just by ramming into it. And for a small object, the answer is yes, that we do have the technology that effectively what it was is terminal guidance. Can you get something that's moving really fast to actually hit a small target right in the middle? And the DART impact showed that, yes, we do have the technology to do that. That only moved it by a few millimeters a second. So that's enough if you have 30 years of warning, right? Because all you have to do is move it by 10,000 kilometers. And so if you can give it a nudge at a few millimeters a second and wait decades, you're in the clear. If you have less warning time or it's a bigger object, then we're talking about possibly using a nuclear weapon to give it a much bigger push. That's untested and likely would never be tested because of the conventions. All the countries have signed no nuclear tests in space. That's a good thing. We shouldn't be doing that. So instead, what we do is every 2 years, the global community gets together at something called the Planetary Defense Conference, where we go through play acting various scenarios. If this was happening and we had this warning, what do we do? If it's small and we have a short warning, then it's civil defense. Then FEMA gets involved and evacuates the local area. If we have a long warning, then we use something like DART. If we have something in between, and so we've actually gone through a number of various scenarios trying to figure out how we would negotiate this on a global scale with our international partners.
How about painting an asteroid?
Painting an asteroid is a viable option. So what you do is you just cover half of it or all of it with reflective paint, and then just the photon pressure alone might be enough to push it off position. That's even slower than DART. So you need a much longer time period to do that. But if you have 100 years, maybe that's the best way to do it.
A few questions. Once you detect these objects, are there terrestrial tools to track them, or is it so much more efficient to use Surveyor? Like, just don't worry about it. You will both track it.
Right. So for NeoWISE, we couldn't point the telescope anywhere else, so we had to rely on our partners on the ground, various telescopes around to follow it. And Surveyor, because we're looking in the daytime sky, we can't rely on ground-based telescopes. The sky's too bright to see it. So we had to design a survey that would follow it, provide enough self-follow-up to establish an orbit on our own. We would love to have ground-based follow-up in a variety of ways. And so we're talking with the various other telescopes about how we can optimize our interfaces between us and them. Yeah.
Second question is in terms of composition.
Yeah.
You know, the scenario like in the Expanse that, you know, are these things really loaded with all kinds of minerals and cool stuff? So someday, 1,000 years from now, yeah, we're probably gonna want to be out there grabbing all that cool stuff to build things.
So there are actually companies right now today that are in asteroid mining and trying to get the startup industry going. The big question is, who's the customer for this? Right now, we don't have a customer for gold or platinum or rare earth elements in orbit because it's pretty expensive to get to orbit and come back. What we might have a customer for is water. Finding a source of water in space for astronauts to use to drink, because people like to drink, to electrolyze and turn into fuel, or just for various other processing purposes. That is probably the most likely way to go forward. And so these new results from Hayabusa 2 and OSIRIS-REx, when they brought back samples of these dark near-Earth objects and found that they're like 7% water by mass. It's a ton of water locked in those dark rocks. And so you could come up with ways of, put it in a solar-powered oven, bake out the water, and extract it pretty straightforwardly. That's looking pretty tempting. So as humanity moves more towards space travel and long-distance space travel, that might be an option. What? And water is a great protector for solar radiation. So if you want to shoot it as a shielding element, you need to have it anyway. So build your tank, live inside your fish tank, effectively.
Cool.
Yeah.
With the exponentially growing number of objects around the Earth that we call space debris, is this making it more difficult to do surveys of NEOs and other objects out there in the asteroid belt? And what can you do with spacecraft to discriminate between what is junk in orbit and then actual objects you want to see?
Yeah, ground-based telescopes, especially the wide field platforms like the Vera Rubin Observatory that'll be coming online soon, are going to suffer from having these bright satellite trails ripping through their images. It's not likely that you would confuse a satellite for an asteroid. Instead, what would happen is you just have this bright streak that washes out a chunk of your data. And so you lose that detection you needed to establish the orbit. Since we're going to L1, we thankfully don't have this problem, but many of my colleagues who work on ground-based surveys are very concerned about the implications of this growing fleet of objects around the Earth have on just dark skies in general, on astronomical research, on human spaceflight. If there is an impact event in there and you start getting more space debris, that can pose a hazard to human health for the astronauts as well. So it is a big concern. And right now, the solution to that likely is legislation, is control by government oversight boards saying that, hey, maybe we shouldn't have free reign to launch everything without a little bit of thought being put forward.
Come to you. Like the solar system, like many of them, and like that orbit, like the asteroid orbits, is that like how it functions, for example, like protection of the whole solar system from like other foreign objects?
Like this one?
Yeah.
So the question is, do the asteroid orbits, are they protected in their orbits? So
protecting like, the solar system from like other foreign objects that's coming from like the outer solar system, or is there any function to that?
No, despite how crowded this plot looks, it's mostly empty space in there. The biggest protector we have is Jupiter. Jupiter's gravity pulls around everything. And so a lot of the stuff coming in from outside that will be stepping in those centaur objects that eventually could step inwards towards the Earth will most likely have a gravitational encounter with Jupiter and be chucked out of the solar system. That Jupiter drives things towards the Earth, but it also drives things away from the Earth. And so it's balanced like that. But the generally asteroids don't affect each other dramatically.
Anybody else?
One up the front.
Oh, Mr. President. you had to start up before, you pointed out the Trojan asteroids in blue. But it looks like there's three levels.
Aha.
Any more from that?
It does look like, so this is the two Trojan clouds on the left and the right here, and it kind of does look that three lobes there, right?
Do those have a name?
Those are the Hildas. So those are the Hilda asteroids. Those are in 3-2 resonance with Jupiter.
Okay.
That is the same resonance that Pluto is in with Neptune. And that's how Pluto's orbit crosses Neptune, but will never interact with Neptune. They'll never crash into each other. It's that same 3-2 resonance. And so if you just plot the Hildas up, they make this triangle on the sky. So in addition to being that lobe at the top, they're also this clump here and this clump here. And you'll see them in the co-moving frame of Jupiter looking like they're drawing a triangle out in the solar system. Yeah.
Joe, I may have missed this.
Yeah.
I've always had a problem trying to imagine all these little rocks, some of them really solid and hard. Our outreach guy on Saturday night, next Saturday, has a 5-pound meteorite that he shows everybody. And supposedly, it's not a giant planet that got broken up into all those pieces, which makes sense to me.
Yeah.
Because that requires a lot of gravity.
Yeah.
How in the world can all these little molecules and dust come together and become something small and then hard?
So yeah, how do meteorites get stuck together? A lot of the things that make it down to Earth, remember, there's a big selection function here. All the weak stuff gets burned off upon atmospheric entry. The stuff that survives most likely was buried under hundreds of kilometers or tens of kilometers of material in an inner part of one of these asteroids. And so there was enough pressure. And in the early part of the solar system, when we still had the aluminum-26 around heating things up, radioactive decay was warming the asteroids, it was warm enough and pressure enough to coalesce into these, strong enough rocks to survive to the ground. When the OSIRIS-REx spacecraft went to Bennu, they had that sampling horn look like kind of a hubcap, and it went down, and it was the way the spacecraft was autonomous. So it was programmed to, when it felt resistance, to wait for a couple seconds and then fire the retro rockets to lift off. When they looked at the data afterwards, it turns out that at the first sign of contact, before they got enough resistance to trigger that return, the spacecraft had actually gone about 50 centimeters into the surface of the asteroid. So that rock was incredibly friable, incredibly crushing. It's basically the same composition as if you go to the beach and the ocean has left that crust of sand that looks solid, but when you step on it, it collapses instantly. That's effectively what the surface of these asteroids, that's how strong they are. Incredibly weak.
Okay, your last chance. In the back. This is the first time everybody watching online has been able to hear the questions from gravity. If we get hit by a loose rubble pile, are we better off than if we got hit by a really solid one?
So yeah, rubble pile or not, that was, so you would think, oh, it's a rubble pile, so it's soft, so it's not as big a deal. However, what we saw if you go to Meteor Crater in Arizona, you have a 50-meter iron meteorite that punched the ground and left a giant hole and scattered meteorites around the local area. Mm-hmm. A little bit bigger than that was the Tunguska impactor that came in over Russia over 100 years ago. That was an airburst. It exploded in the air because it was weaker, because it was probably a rubble pile of some kind. And instead of making a hole about 1 kilometer across, it leveled a chunk of forest about 30 kilometers across, the size of a city. And so, as our colleagues in the nuclear weapon industry have discovered, airbursting is much more effective at destroying things than coming all the way down to the ground. And so, unfortunately, no, the rubble pile potentially could level a much greater area and cause significantly more ground damage. It's also the harder one to interact with. How do you push a pile of sand around? If you want to land on it and attach a rocket motor and blast off with it, how do you attach to it? How do you interact with that body? That's one of the difficult problems. So the rubble piles are actually the most concerning objects that we have to deal with.
Anybody else want to talk? Well, next month, yes, Okay.
Yeah.
10 o'clock in here, so we're in good shape. Thank you. You mentioned a couple times about using the thermal environment to test the cooling in the family.
Yeah.
We saw James Webb as a pretty complex thing. What is the thermal environment?
So the thermal environment where we are L1 is pretty much the same as where James Webb is at L2. There, L1 is only 1% closer to the sun than we are right now, so it's about the same. The difference is that we can operate at around 40 Kelvin and still get good data. Webb needs to be at a few Kelvin. And that is a wildly different regime in terms of cooling. They also had a wildly much more expensive telescope, and so they could afford very expensive cryo coolers to get themselves down to that temperature and have the telescope separated away from the spacecraft, because cryo coolers are refrigerator pumps effectively that are doing this and shaking. And so you don't want your telescope optics shaking, so you have to separate that, vibrationally isolated. We went with the other option, which was have radiators painted in very, very black paint that's black at all wavelengths, so that it just dumps heat into the void of space. It's slow. It can't respond well if we accidentally point at the sun. It's very bad because they're really good at absorbing heat too. But as long as there's no problems and it points at the deep of space, it will maintain that nice temperature for the entire length of the mission without any fancy machinery and without any lifetime limiters.
Thank you.
You're welcome.
And thank you. I'm going to tell you next month, our topic is going to be dark matter. I don't know what the pictures on the screen are going to be like. Give me that young guy from the UCSB.